All right, now that we've had an opportunity to explore both exponential and logarithmic functions, I wanted to do some problems that involve exponential models of growth and decay, and also briefly talk about logistic growth. So let's go through the various different kinds of exponential growth and decay. So first off, let's look at exponential growth. For exponential growth, we would see something that looks something like this, now that I got this settled. A times e to the bx power. So in this case here, b has got to be greater than 0. So what does this exponential growth problem look like? Well, we know that when our x value is equal to 0, this is going to be equal to 1. When our x value is equal to 1, our output is going to be the value of e, which is about 2.718. So this function is going to look something like this. So we graphed something pretty similar last time when we were talking about the graphs of the natural number functions. So if you look at this kind of carefully, we'll see that we've actually seen this model before. If you think back to the continuously compounding interest problems, we saw something that looked like this, what we call the A PERT, where our P is our principal amount. So in this case, that would be our A value here. Our R is the rate at which this is changing, so that would be our B value here. So in this case, we have B that's greater than 0. And then our T value is the amount of time or what the independent variable is. We say that it's a function of time. In exponential growth, it's a function of x here. Now, don't worry too much about why the base value is e right now. Just know that when we are dealing with population growth or exponential growth, we will typically use a base of e. And the reason for that has to do with calculus. You'll learn about it a little bit more when you get to calculus, but the short answer is that it has to do with the instantaneous rate of change, and e is the only value such that the constant is going to be 1, so that our instantaneous rate of change gives us the same value. Again, don't worry too much about that, but those of you who are wondering, that's why we use the base of e. So what are examples that would be using exponential growth, or when does exponential growth occur? In problems that deal with things like population growth, for example, and this can include, human beings. It could also include bacterial or virus growth. You might also see something with like continuously compounding interest. Those would be cases in which we would see exponential growth. Well, what about exponential decay? When does that occur? Well, exponential decay, I'm going to write this as the following. Now, you could also write this so that b is less than 0 and just use the same structure as the first one. But the reason why I'm doing this is because I want to highlight that this is simply a reflection over the y-axis. In other words, this graph would look something like this. So we're going to see a function that looks something like this here. Okay, so this would be an example of exponential decay. Namely, just understanding that this occurs. The way I've written it, I'm writing b is greater than 0, but understanding that means when we have negative b here. Okay. What would be examples of exponential decay? You could see things like half-life or radioactive decay, or something like even depreciation, which is simply the idea that something loses monetary value or just loses value over time. So things like a car. If you buy a car, that car is going to depreciate rather quickly. That is to say, it's going to lose its value at a exponential decay rate, not so much at a linear rate. Finally, logistic growth, is going to be something like this. And the way a logistic growth problem is going to look, it's going to start off looking somewhat exponential, but over time, it's going to then become something more logarithmic. So something like something that looks something like that. Okay, something that's going to have a rapid growth and then a declining rate of growth. So I'll write that, a rapid growth and then a declining rate of growth, I should say, declining rate of growth. And this is more kind of realistic as to how populations actually grow when you take into account things like resources. So for example, if you looked at the number of fish in a pond or in a lake. You might see a huge growth rate initially, but as there are limited resources, the number of fish that can be in that pond at a certain time starts to reach kind of like this upper bound, if you will, or this almost kind of like a horizontal asymptote here. We would call this our upper bound. Okay. All right, so these are the various types of exponential models that we will be working with in this particular lesson. We're going to just try a couple problems, but a few things for us to just keep in mind as we work through this. Number one, do not round. Do not round as you go. You want to save your calculator use, and you will need a calculator for this lesson, so go ahead and pause the video and get it handy. But if you are entering in rounded values as you go along, you are not going to get a precise answer. So don't round as you go. And then secondly, let me make that star a little bit better as well. Secondly, we want to answer in complete sentences in the context of the problem, in the context of the problem. Okay, so complete sentences in the context of the problem. So for example, if you're dealing with counting the number of humans or people in a particular problem, you wouldn't want to give me an answer or give an answer that would have decimal places. You would want to round, depending on the context of the problem, round down or round up to the nearest person. If we were seeing a problem that involved money, you would want to round that to dollars and cents, if that makes any sense. Pardon the pun. But with that said, let's just try a couple practice problems here. Okay, let's look at this first problem. The population P of a city is given by this function here, where T is equal to 0, and that is on January 1st, 1996. When did the population reach 150,000? So a couple things that are actually missing here. One, I should note that T is in years. And the second thing that I should note is I want to give my answer in the month of the year where this occurs. So we're going to give our answer in the month of the year that our population reaches 150,000. Well, if we know our population function and we're trying to see when it's going to reach 150,000, we're effectively solving for t. So let's plug in what we know. So we can say 150,000 is equal to this. And we are going to solve this exponential equation, which we practiced in our previous lessons, to solve for t. This is what we're going to be solving for. So we're going to isolate our exponent. So we're going to divide both sides by 95,000. And I know you might be tempted to just grab your calculator right now, but I'm going to try to simplify this as much as I can so I have an exact value. Divide both the numerator and denominator by 5, and we should get 30 over 19 is equal to this. And we learned when we're solving exponential equations, we're going to take the natural log of both sides. And then from here, that allows me to use my logarithmic property to rewrite this as a factor or a scalar. So I can then say the natural log of 30 over 19 is equal to 0.055t. Now from here, I just need to divide both sides by 0.055t. And let's just go ahead and delete that on this side or erase that from this side. And this is our exact value. But let's go ahead and approximate this. This comes out to be, let me actually write this here. This comes out to be t is approximately, pause the video right now and go ahead and enter this into your calculator. But hopefully you find that you should have gotten 8.304. Okay? Now think about this for a second. We wanted to give our answer in the month of the year, and we know that t is already in years. So first things first. I'm going to start writing my sentence. I'm going to say the population, and I can abbreviate here, will reach, or since it's actually past tense, we can say reached 150,000 in, and let's write the month here of, and the year. So let's focus on the year first because that's pretty easy. If we know that this was 8.3 years, and you know that it's t is equal to 0 is on January 1st, 1996, well, 8 years, that means now we have to be in the year 2004. That's 8 years after 1996. Now what about the 0.304? Now this is 0.304 of a year. So since I want to figure out the months, I'm going to do 0.304, and I'm going to multiply it by 12, and you should get something like 0.366, I think. Okay, and think about this for a second. If January 1st, if t is equal to 0 is on January 1st, when t is equal to 1, you're at February 1st, meaning 1 month has elapsed. T is equal to 2 is March 1st. T is equal to 3 is April 1st. So 3 months have elapsed, and we're partway through the month of April, so we can just say simply April of 2004. Okay, because we haven't made it all the way through April. We have not finished that whole month. Okay? All right. I have already done a compounding interest problem in our previous lesson, so I'm going to go ahead and skip. Actually, you know what? I don't know if I ever recorded that lesson problem. So let's do this one then. For savings account with compounding interest continuously, we have $1,000 invested. Okay, so we're going to use this APERT formula. Oops. 10 years later, the account balance is $1733.25. What is the interest rate? So in other words, we need to solve for R. Okay, the nearest hundredths place. All right, so let's go ahead and do this. So let's plug in what we know. We know that we started out with $1,000. We know we're going to be solving for R, and we're trying to see when it becomes $1733.25. And what other information are we given in this problem? If we go back here, it says 10 years later. We know that. So t is equal to 10. T is equal to in years. Or t is in years, I should say. So now that we have that, let's solve for R. So now, again, we have an exponential equation that we need to solve. We're going to start by dividing everything by 1,000. Okay, so this is 1.73325. This is equal to e to the 10r power. So to then get r by itself, I'm going to need to apply the log property. So I'm going to take the natural log of both sides, which then allows me to rewrite this as the natural log of 1.73325 is equal to 10r. And again, what I did was I applied the log property there. Then we're going to divide everything by, oops, not r, by 10, excuse me. We're solving for r. Okay, so r then is simply equal to all of this. So what is r approximately? Now go ahead and we put that into our calculator. We should get approximately 0.054999, which let's round that to the nearest hundredth place. Well, we'll actually use this because we can say r, if we're writing this as a percent, we want to move this over to, so we would say 5.4999. Let's round that there. So if we write our answer as a sentence, the annual interest rate is approximately 5.500. What's that hundredths place? So I guess I can just write there 5.50%. There's our annual interest rate. Okay. All right, let me do one more problem with you to really hammer some of these concepts home. The spread of a virus on a college campus of 7,500 students is modeled by this equation, which if you notice the structure, we are talking about a logistic growth situation. We're talking about logistic growth here. Okay. Where y is the number of students infected, I should say, after t days. The college will cancel classes when 30% or more of students are infected. So when is that going to happen? After how many days will the college cancel classes? So as we have done so far, let's plug in what we know. If we are talking about 7,500 students, we want to know, when is the college going to cancel classes? Well, when 30% or more of the students are infected. So what is 30% of 7,500? That's going to come out to 2,250. So in other words, the college isn't going to cancel classes until 2,250 students are infected. So that's the number that we are setting in place for y. Oops. There we go. And we've got another exponential equation that we need to solve. So let's multiply both sides by the denominator. Here. And we got 1.7499 e to the negative 0.9 t is equal to 7,500. And then we are going to go ahead and divide both sides by 2,500 now, or 2250, excuse me. Okay, and we got this. And if we simplify that right side, 7,500 divided by 2250 is just going to be 3 1/3, so we can say 10 over 3. And then subtract 1 from both sides. That's going to be 7/3. Now we can divide everything by 74.99. And we can say that e to the negative 0.9 t power is equal to, let's write that as a non-complex fraction. So 3 times 74.99 is 22,497. And now we can take the natural log of both sides. So take the natural log of this left side, take the natural log of this side. And this is going to come out to negative 0.9 t is equal to the natural log of all this. Which again, now I'm going to divide everything by negative 0.9. So from here, we can say this is the t value, which comes out to approximately, and let me just punch this into my calculator myself. We should get approximately 8.972 here. And t is in days. Now, that's not how we write our final answer. Let's answer the question, and let's put that value in the context of the question. The college cancels classes after this many days. Now, pause the video and ask yourself, how many days would this be? And we would say 9 days. Now, we're not rounding up to 9 because it's closer to 9 than it is to 8. In fact, even if our value had been approximately 8.02, something that's barely above 8, we would still say 9 days. And the reason for that is if we round it down to 8 days, right? Ask yourself, have we reached that 30% threshold? And the answer is no. That doesn't occur until after 8 days have passed, right? So they won't be able to cancel classes until they reach that 30%, which means it's got to occur after 9 days. After 8 days, it's not enough of a infection spread and for them to cancel classes. So it doesn't really matter, this value, just as long as it's above 8, we know that the cancellation won't occur until after 9 days, okay? So as you work through the rest of these problems here, really just ask yourself, what do I need to do, or what is the context of the problem? When would I round up? When would I round down? And it's not always just about the numeric value, but about what makes sense in the context of the problem being asked.